Okay, in a certain community, %36% of families own a dog, and 22% of the families that own a dog also own a cat. In addition, 30% of the families own a cat. Find the following. So the first part is find the probability that a randomly selected family owns both a dog and a cat. Okay, so we have 36% of families own a dog. 22% of the families that own a dog also own a cat. 30% of all families own a cat. And the probability is if you select a family, what probability is it that the family owns both a dog and a cat? So this is something that we've seen in the previous lecture. I think we've done actually a little bit harder example last time. So this is a typical conditional probability problem. So again, the most important thing, first of all, is to define your events. So what should we define our events to be? Anybody have an idea? Where should we begin? How should I define my events? I can call them A, B, C, D. Let's be consistent with D and C. So what would D stand for? What would make sense for D to stand for? It's the event that what? Event that okay, so D is the event that a family owns a dog. That's right. That's the event. And then associated with that event is a probability, isn't there? The probability that D occurs, which is the probability that the family owns a dog, is given by this first little phrase here. So the first information that we have here. So this here is the probability that D occurs, which is 0.36. So remember, we convert our percentage, we convert it into probability because probability is between 0 and 1. So we have our first piece of information, and then what follows is that the event that a family owns a cat is the probability that C occurs. And what is that probability? .22. Now, be very careful. Look what the 0.22 or the 22% refers to. It refers to the families that already own a dog. And those that own the dog already own a cat, right? So this information below that says that 30% of all families own a cat. So this is the probability that C occurs, which is 0.3. So this is 0.3. So what is that 0.2% then? 0.22%. What is that referring to? Does anybody know what this 22% of all families that own a dog also own a cat? So that's a little different, right? How do we, is it the intersection? So also be careful with the wording. Look what part A says. Part A says the probability that you randomly select a family that owns both a dog and a cat. So in other words, this question is asking, what is the probability that D intersects C? That's our question. So 22% is not what we're trying, it's not what we're trying to find. 22% is what Ethan just mentioned. That's right. The probability that this is the probability that you have a cat given that you already own a dog. So in this case, we're given the conditional probability from the beginning. The probability that you own a cat given that you already own a dog is 0.22. So this is the probability that family owns a cat given that they already own a dog. And so how would we now, given the information that we have, how would we find the probability that D intersects C? Anybody? Well, we used algebra. Saring, yeah, of course, algebra works, right? But there's a formula that we haven't necessarily used as much. But if you notice, look at this formula. This is the formula that utilizes that you can use to find the intersection of two events when you have a given probability. So here, look what we have. We have the probability that D intersects C. What I can do is I can find the probability that D occurs, multiply by the probability that C given D occurs. You see how this is consistent with this formula? The probability that A intersects B is equal to the probability that B occurs, multiplied by the probability that A given B occurs. So in this case, the probability that D intersects C is equal to the probability that D occurs times the probability that C given D occurs. And we already know what probability of D occurring, it's 0.36. And then we already know what probability of C given D occurs is 0.22. And when you multiply 0.36 with 0.22, you get 0.0792. And this would be your final answer. Probability that D intersects C is equal to this probability, which is approximately 7.92%. So 7.92% of the families owns both a dog and a cat of all families. Okay, that's what that means. Okay, so that's that. So that's part A. Now part B asks, find the conditional probability that a randomly selected family owns a dog, given that it owns a cat. Now we want the other probability, conditional probability. So what am I looking for? The probability that we own a dog, right? So it's like the opposite of this. When you switch around the letters, we want the probability that you own a dog given that you already own a cat. So this is what I want to find. Now, how would I proceed with this? Don't I have enough information to figure that out? Yes, okay. So then how would I find it? What formula would I use, or how would I utilize the formula to find a probability that D given C? Just divide C from our previous answer. That's right. That's right, because the probability that D given C is equal to what? The probability that D and C occurs divided by the probability that C occurs, actually. So then we already found part A, that the probability that D given C is 0.0792. And then we're going to divide off by what? The probability that C occurs, which is 0.3. And then when I divide 0.0792 divided by 0.3, I get 0.264. That's it. So like I said, this is a relatively simple example of utilizing conditional probability with the intersection of two events. Okay, so any questions about this problem? We're good with this? Yes. Okay. So that's like the basics of conditional probability, and we're going to work our way to what's called Bayes' formula, but we're not there yet. I do want to look at one of the problems in the homework, just one of them. It's because it's a little distinct from the rest of them, the rest of the problems that you have for homework. So let me just look at it. So it's problem number 18 in homework number 1. It's not a hard problem, but it's a good problem that that makes it good. So this is homework number 1. Problem number 18. And why am I doing this now is that I want to talk about the partitioning of a set, partitioning of an event, partitioning of the sample space. This is an example of that. And we did talk about partitioning, but in a very general sense and we just drew stuff out. And it was a very brief Like I just said it very briefly. So here we have events A1, A2, and A3. So this phrasing is very important. Events A1, A2, A3 form a partition of sample space S. Now I want to draw this sample space as a rectangle. So my sample space is everything that can possibly occur in my probability experiment. And then A1, A2, and A3 are partitions. Now, does anybody remember what that means to partition a sample space? What does that mean? When you partition a sample space, or when you partition this region, what would that mean? So mutually exclusive, right? So each of those events cannot occur at the same time, which visually means I'm literally just dividing. I'm dividing out, I'm carving up. It doesn't have to be straight, it doesn't have to be curved. I'm just carving up this sample space into 3 distinct regions. This is going to be A1. This whole region here is A1. This whole region here is A2. And this whole triangular region here is A3. This is just an example, right? So then what do we say? A1 and A2 is empty. The intersection between them, A1 intersect A3 is empty. And then A2 intersect A3 is empty. They're all empty, which means that A1 through A3, they're all mutually exclusive events, right? So A1, A2, A3 are all mutually exclusive events. And not just that, but A1 intersect A2, union A2, union A3. What do these unions become? If I put A1, A2, and A3 together, it gives you exactly. It gives you the sample space. So be careful, Saring. It's the probability that this, right? It's the probability that A1 union A2 union A3. This is equal to the probability of the sample space, which equals 1. So the union is not 1. The union is the sample space. The probability of that union, which is a sample space, is 1. So all of this, guys, all of this is what it means for A1, A2, and A3 to partition a sample space. That's what it means. Okay. Now, the probability that E occurs, right? That's what we want to find. So where's E? E is just some event. And I'm going to draw this with this blob here. It's just some event. And I don't know what probability of E is, but what I do know is the probability that E given A1. I know this is, for you guys, it will be different numbers. This is 0.1 for me. The probability that E given A2 is 0.3, and the probability that E given A3 is equal to 0.7. So you have these conditional probabilities. You also have the probability that A occurs, which is 0.1. Probability that B occurs, the probability that A2 occurs is 0.4, and the probability that A3 occurs is 0.5. Now, how would I find the probability that E occurs? Does anybody have an idea for this? So if you notice, probability of E, there's an over that it's overlapping A1, A2, and A3. So Alexandra, add what exactly? What do we add? So we do add, I don't know if you mean to say you add the probabilities of EA1. These probabilities? Okay. But you're missing something if you were to do that. You would be missing something. What would you be missing? Well, let's look at this region here. What is this region called? How would you label this region here? Given the sets E, A1, A2, A3, using these sets here, how would you label this region right here? Is this E1? No, don't use E sub 1. You don't need to use extra ways of separating E. Just use E and use A1. Right, Fang, that's right. This here is E intersect. This here is E intersect A1. That's this region. It's the intersection of E with with A1. That's what this region is. And then you guys follow what happens after. Then what is this region here? You can't call it E1, but then the more specific way is E intersect A1. This would be what? E intersect A2. And then lastly, this would be E intersect A3. Does everybody follow? So in the way I use the partition to also partition the smaller event E. I'm also using the same partition for S to partition out E. So you notice A1, A2, A3 are all mutually exclusive. And then because of this mutual exclusive way of dividing up the sample space S, E can also be expressed as a union of mutually exclusive sets. So do you notice that the probability of E would be the same? It would be the same if you take the probability of A intersect A1, right? And that's one set. I'm going to union that with the probability with the set E intersects A2 union E intersect A3. Does everybody follow what I just did? I rewrote E as a union of mutually exclusive events. And each of those events are written in this way. Now, because these are mutually exclusive, let me just write that. What do we know about mutually exclusive events? If you want to find the union of mutually exclusive events, I just using the axiom number 3 of the probability axioms, right? I can find each of them individually and add them up. Whoops, that's the other way around. So this is plus the probability that E intersect A2 plus the probability that E intersects A3, right? They're mutually exclusive, so I can just add up when I have the union. Now the question becomes, what is the probability of E intersect A1? How would you find the probability that E intersects A1? That's right. Now we use that formula again, right? With the conditional probability. So we know that the probability of A1 multiplied by the probability that E given A1. And what is that? That is 0.1 multiplied by 0.1, and you get 0.01. Do you see that? So we got our first one. We got our first probability. So I'm gonna call this is 1. Now let's look at 2. So the probability that E intersects A2 is equal to the probability of A sub 2 multiplied by the probability of E given A sub 2. What's the probability of A2? 0.4. And then what's the probability of E given A2? 0.3. And then when you multiply 0.4 with 0.3, you get 0.12, right? And then lastly, probability that E intersect A3 is equal to probability of A3 multiplied by probability of E given A3. 0.5 multiplied by 0.7, which is 0.35. And then when you put that all together, so now the probability of E is equal to the probability of A1 times the probability of E given A1 plus the probability of A2 multiplied by probability of E given A2 plus the probability of A3 multiplied by probability of E given A3. When you add these up, you get 0.01 plus 0.12 plus 0.35. And adding them up, 0.01 plus 0.12 plus 0.35. And the resounding probability is 0.48. So any questions about the probability of E? Clear as day. So the idea, guys, is the partitioning of S with mutually exclusive events also partitions the event inside of S, a smaller event. And you're able to partition that event using the intersection of those mutually exclusive events. In doing so, we're able to find a probability of that event. So what does this illustrate? This illustrates a principle. It's called the law of total probability. And this will become very important when we talk about conditional probabilities. So it says that if you have mutually exclusive events, let me just get the right formula for this. Yes, so the law of total probability says the following: if events, I'm gonna call it A sub I, right? A sub I, where I goes from 1 all the way through n. So if you have n mutually exclusive events, so if A1R mutually exclusive events and I'm going to write it as the union as I goes from 1 through n. So if you take the union of all the AIs, this gives you the sample space S. Then if E is an event in the sample space, then the probability that E occurs is equal to the probability, right, that E intersect A1 occurs plus the probability that E intersect A2 occurs all the way to the probability that E intersects AN. But this here is written as what? The probability that A1 multiplied by the probability that E given A1 occurs. That's the formula for that. Then similarly, probability of A2 times the probability that E given A2 occurs all the way to the probability of A sub n multiplied by E given A sub n. But instead of writing all this out like this, I can use summation sigma notation, right? And I goes from 1 through n of the probability of A sub I multiplied by probability of E given A sub I. And this is the law of total probability. Okay, so keep that in mind, that if you have mutually exclusive events that make up a sample space and you're trying to find a probability of an event in that sample space, you can use the conditional probabilities with A sub I to figure out, it's like all of these are little pieces to the puzzle, and when you put them all together, you get this complete event, the probability of that complete event occurring. All right, so any questions about law of total probability? And the rest of the problem, for example, so it asks, the next thing is to ask probability that A sub 1 is equal to the probability of A sub 1 given the probability that E happens. Now, how would I do this one? And the other two are exactly identical. Anybody? Did I lose you guys with the law of total probability? Probability of A sub 1. Right. The probability of A sub 1 intersect E, right? All over the probability of E. This is straight, this is directly from the formula for conditional probability, correct? That's what you applied, Fernando, which is great. But then now the question becomes, what's the probability of A intersect E? So I found this already from the previous example, right? I used the law of total probability to find a probability of E occurring. But what is this here? And Zering says 0.1. So are you sure it's 0.1? I think you're close though. So how would you calculate this? Didn't we calculate this here? Probability of E, so E union A1, isn't it this? 0.01? But the idea, guys, is that eventually we'll unpack this now. This probability that E, right? Given A1, multiplied by probability that A1 occurs. And so for now, I'm just gonna write it like this, right? It's so you just use the numerical value. So 0.01 is the top, and then 0.48 is the bottom, right? Because we found it. So when you divide that, 0.01, it's going to be a small decimal, 0.48. You get 0.0, you get 0.208 3 repeated, right? That's what you get for the probability of A1 given E. And I'll stop there with the homework problem because the rest of the problems are exactly alike. But I do want to unpack what we just found. The probability that A1 given E occurs is equal to the probability of A1 intersect E over the probability that E occurs. So this problem is very nice because this talks about a formula. So this is a formula that we're coming up with. This is the probability that E given A1 occurs multiplied by probability of A1, right? That's the top formula. And the bottom formula, how do we find it? We found it by the probability that E given A1 times probability of A1 occurring plus the probability of E given A2 times the probability of A2 occurring plus the probability of E given A3 multiplied by probability of, let me scoot this over a bit, the probability that A3 occurs. And this, my friends, is what's called Bayes' formula. This is an example of what's called Bayes' formula. I think it's an English mathematician, Bayes. So this is the formula we're going to start using a lot more of, Bayes' formula. And Bayes' formula is a probability of an event occurring given that a event already occurred, right? But this event is kind of like an event in the future, and you're trying to find an event that, what will be the probability that this event occurred in the past? It's one of those kind of probabilities. You're given something that would occur. So E usually occurs after A1, usually. So then it's like, oh, if this event occurred in the future, or if this event occurs after A1, then what's the probability of that A1 occurred? That's the idea behind this formula. Okay, so let's see it in action with an example. Okay, so on rainy days, Joe is late to work with probability 0.3 on non-rainy days. And he is late to work with probability 0.1. With, sometimes the wording is a little strange, right? With probability of 0.7, it will rain tomorrow. So then the question is, find the probability part A, that Joe is early tomorrow. So how do we break this up? What do we do? So we have several probabilities, right? One probability is that he's late to work with probability 0.3 on non-rainy days. He's late to work in general with probability 0.1. With probability 0.7, it will rain tomorrow. And now ask, find the probability that Joe is early. So I want to find what's the probability that he's early tomorrow. Not today, but tomorrow. In general, he's late with a probability of 0.1. So let's do this. Let's call late. So let L be the event that Joe is late. So the sample space is a space that Joe gets to work. Yeah, that's one way to think about it, right? Like he's gonna go to work, right? As it reads on rainy days, he's late to work with probability 0.1. Oh, you're right. I missed I missed the punctuation. I missed the punctuation, Alexander. It says Joe is late to work with probability 0.3 semicolon. Sorry about that. There's a semicolon right after that. And then on non-rainy days, he is late to work with probability 0.1. So yes. Yeah. I missed that semicolon there. So that's important, guys. The wording, the English, the punctuation, the phrasing matters a lot in these problems. Okay, so I'm gonna write that L is the event that Joe is late, right? And then I'm gonna write E is the event that Joe is early. And then I'm gonna write R is the event that it rains. And I write N, I guess, as the event that it doesn't rain. So being able to first express your sets just the way that they're given in the form in the work, right? In the problem. They don't tell you this explicitly. They just tell you probabilities of certain events occurring. So what you have to do is see, okay, how can I how can I write out what the events are? So either Joe goes late to work or he doesn't go late to work, which is meaning that he goes early to work or on time. And yeah, I don't think it's talking about being on time, right? So yeah, so it's either he goes to work early or late, and it either rains or doesn't rain. So those are the four different possibilities of stuff happening, right? And what information do I have? It says on rainy days, he is late to work with probability 0.3. How do I break this down? How would I express this first phrase here? On rainy days, Joe's late to work with probability 0.3. Given these letters that I have here, these events that I've just delineated, how would I express that first statement here? So I'm gonna write this as call this one. So what does one say? How would I write one? L intersect N. Hmm. So the probability that L intersects R, is that what you're saying? Is 0.3. Okay. And then on rainy days, he is late to work with probability 0.1. So then what do we have there? So this number here, number 2. So he's late to work. And L, right? So the probability that he's late to work, non-rainy days, is 0.1. And then with probability 0.7, it will rain tomorrow. So that last statement here, what does this third statement here say? The probability that what will happen? Probability that it would rain, right? Is 0.7. So if it rains with the probability of 0.7, what does it mean? Do I have any other information that stems from it? And I think we have to rewrite this first two statements, but this last statement, probability that it rains equals 0.7, right? Do I have any other information? Right. So then, okay, guys. So one thing, right, is that R and N are complements of one another. So these are complements. Complements of one another. What that means is that the complement of N that it doesn't rain is that it rains. And the complement that it doesn't rain is that it doesn't rain. Okay. And what do we know is that the probability that N, right, is equal to the probability that R complement, which is equal to 1 minus the probability that R, right? Which is 1 minus 0.7, which is 0.3. Okay, so that's important information. Now I got those two things. I got the probability that it rains and also got the probability that it doesn't rain immediately, right after. And then what's the question asked? Find the probability that Joe is early tomorrow. So I want to find, part A asks, I want to find the probability that Joe is early. Just that he's early. Now, using the law of total probability, right? The law of total probability, what would this look like? How would I find the probability of E? How would I find it? How would I find the probability that he's early? What would I find? I find the probability that he's early intersect what? That it rains, right? And then probability that E intersect that it doesn't rain. Remember, we partition the sample space utilizing mutually exclusive events. If you're the complement of one another, they're mutually exclusive. Do you guys see that? It's like I'm dividing up the sample space between non-rainy days and a rainy days. And then within this, I have an event, right? That he goes to work. But either he goes to work late, he goes to work late, or he goes to work early. But that's dependent upon whether it rains or it doesn't rain. You guys see that? So in reality, this is do I have this information? Do I have E intersect R? Do I have E intersect N? I don't, right? So then what do I do now? I have to find a probability that he's early given that it's rainy. What's the probability of that happening? That's it to multiply by the probability that it's rainy plus the probability that E intersect N, given N. So given that it's non-rainy, what's the probability of him being early? Multiply by the probability that it doesn't rain. This is the law of total probability. Now, I think looking back at this, it says that he's late to work on non-rainy days with probability 0.3. So I know it doesn't say it, but it's kind of implying it, right? That it is given it's like given a rainy day, Joe is late to work with probability 0.3. So on rainy days, he's late to work with probability. Yeah, so he is late with this probability on rainy days, right? So this should be changed to he's late given that it's rainy. And then it says on rainy days, he's late to work with probability 0.1. Okay. So this is what we have so far. We have this, right? Which is what? Probability that it's rainy is 0.7. We have this, the probability that it doesn't rain is 0.3. So now the question is, what's the probability that he's early given that it rains? Now, what do you guys think? How can I figure out the probability that he's early given that it rained using the information that I know that he's late given that it rains?
Professor?
Yes.
I think the last probability that it's not raining is supposed to be 0.1, right? P of n is,
Say that one more time.
right, on non-rainy days, it's 0.1, not 0.3. P of n at the very bottom.
No, I think it is 0.3, right? P of n. P of n is
I think I'm confused what
About
you're. So if you scroll to the top, it says on non-rainy days, he's late to work with a probability of 0.1, right? That's n.
No, that's not n.
Can you explain that again?
Yeah.
Okay.
N. So the way I defined n was that it's the event that the day doesn't rain. N. So
Right,
n
non-rainy days.
is the probability that it doesn't rain.
Right.
R is the probability that it does rain. So I'm given the fact that it rains with probability 0.7. So if it rains with probability
get it.
0.7, then the complement would be 0.3, which is the probability that it doesn't rain.
Okay, I got it. Thank you.
Right. And so that statement here, on non-rainy days, he's late to work, implies that given that the day is rainy, non-rainy, what's the probability of him going or late to work? Is 0.1. So that's the statement here. Okay. And so then what I'm asking though is, given the fact that I'm given the probability of him coming late to work on a rainy day, what's the probability of him coming early to work on a rainy day? So do you guys see the connection between late and early? They're complements. Well, you can say that, right? I think the assumption is that they're complements, because you can also say, what if he's on time? That can also be part of the complement of being late. But I think for this simple example, the assumption is that they're complements. So then what's the probability that E given R? That's another thing. This now is a new probability space, right? This, when you do conditional probability, this is like my new sample space, right? Rainy becomes my new sample space. So in the sample space, the probability that L occurs is 0.3. So the probability that the complement of L would be what? 0.7. And then what's the probability that he's early given that it doesn't rain? 0.9. So then that's the information that I'm given that I'm able to figure out from the given information. So this is 0.7 multiply 0.7 plus 0.3 multiplied by 0.3. So what am I given here? What do I find? What do I find? 0.7 times 0.7 is 0.49, right? Plus 0.3 times 0.3 is 0.3. And so he's early with what? 0.58, right? So he's nearly half the time he's early. Does that make sense? 0.9 times 0.3, where is that? Oh, pardon me, you're right. I don't know why I wrote that. You're right, it's 0.9, sorry about that. So then 0.9 times 0.3 is what? 0.27. And then when you add this up, what do you get? That was my mistake, 0.76, right? So I know this is kind of new. This is very new, right? So we talked about mutually exclusive events, partitioning of a sample space. We talked about separately conditional probability, just the very standard basic formula for standard conditional probability. And now when you connect those two things together, we have this thing called Bayes' formula. And we're using what's called the law of total probability here. So the probability of an event that he comes early is dependent upon two mutually exclusive events, which is whether it rains or it doesn't. So to find a probability that he comes early, you have to find a probability that he comes early with the fact that it rains, and a probability that he comes early with the fact that it doesn't rain. So in this probability that we found, we have to find what's the probability that he does come early, given that it does rain, multiplied by probability that it rains, plus the probability that he comes early, given that it doesn't rain, multiplied by probability that it doesn't rain. So do you see how we have to include all these probabilities together just to figure out this probability that it does come early? So this is, again, the law of total probability. That's how you solve part A. So, and again, the assumption, we made an assumption, and that's the assumption that's kind of expected for you to say, is that being late and being early are mutually exclusive, are complements. And that's why we're able to say that the probability that you come late given that it rains is 0.3. And then immediately we say the probability that it come early given that it rains is 0.7. So in this sample space that it rains, these are the complementary probabilities. But if you really want to be strict about complement, then the complement that someone is late is that he comes early or he comes on time. But we don't have that information in this problem. So we're not saying that he comes on time. So he either comes early or late. I think that's the assumption we can make, and that's safe to say. But any questions about this? This is going to take some time to internalize, to understand, and to be able to apply it for future problems. But this is like a new way of approaching a probability problem. And now the next problem associated with this problem is, what's the probability? So given, so do you see this here? Given that Joe is early, find a probability. What is the probability? What is the conditional probability that it rained? So do you see how we've used the fact that it rained to see what's the probability of him coming early or late? Now we're going to ask the opposite question in reverse. So given that he did come early in this case, what's the probability that it did rain? Because if he came early, if you just know the information that he came early, well, it could have rained or it could have not rained, right? So what's the probability that if he did come early, what's the probability that it did rain? That's what we use. So we use here Bayes' formula. So then how would I express this probability? So what am I really looking for? The probability that what slash what? Yes, P, R, and then given Joe's early, right? So that's going to be, I can't do this. Well, I can do this, right? I can't do probability of R intersect E over the probability that it's equal to E, right? Probability of E. But I already found this in part A. Found in part A. Just to give you the formula. So conditional probability, Bayes' formula is really a kind of like an unfurling of conditional probability. So if you know conditional probability, you can kind of hedge your way into Bayes' formula. Probability of E is the probability of E given that that it was rainy times the probability that it rained plus the probability that he's early given that it's non-rainy, probability that it's non-rainy. Now what's going to be the top? What's going to be the numerator? So you can write this in various ways, right? There's two ways to write the intersection. Either you write it as the probability that it rains given that he's early, probability that he's early, or you can write it as a probability that he's early given that it rained and multiply by probability that it rained. These are two ways to express the probability that it rains intersect probability that he's early. Do you guys see that? There's two ways to express that with two different conditional probabilities. So which one of these conditional probabilities do I have? Do I know it? Do I know the probability that he's early given that it rained? Or do I have the probability that it rains given that it's early? The second one, right? Because this is exactly what I'm trying to figure out. So it's not going to help me if I use what I'm trying to figure out. I have to use what I already have. So this is the probability that he's early given that it rains, multiplied by probability that it rains. And if you notice, this statement here is also here. It's just that in the denominator, we have the additional set that it doesn't rain. So this is already here, which is part of the formula. So I know the probability that he's early given that it rained, right? At 0.7. The probability that it rains is what? 0.3. The probability that it's early, he's early given that it rained, 0.7 times 0.3. The probability that he's early given that it didn't rain was what? 0.9. And the probability that it does not rain is 0.3. But again, I already found this in part E, which was what? 0.76. And then the top here will be 0.27. And then when you divide this, 0.27 divided by 0.76, I get 0.355. 0.355 dot dot dot. I'll just leave it with the 2 decimal places. Point, I think this is 49. Yeah, the probability that it rains, right? What's the probability that it rains? Yeah, 0.27. So you can also write this as a decimal here. I mean, as a fraction, 27 over 76, which is 0.355. Wait, why is it 0.3 for rain? Oh, you're right. Yes, pardon me. This is 0.7. You're right. 0.7. Again, we did this one in part E already. I mean, part A already. So this is 0.76 from this part here. You're right. Yeah, and you're right. It should be 0.7, not 0.3. Thank you, Fernando. You caught every single oh, Ethan got it. Yeah, thank you, Ethan. So any questions about Bayes' formula? So would you guys be able to find the next one? Given that Joe is late, oh, I see what you're saying. So this should also be part of, it should also be 0.7. Is that what you guys are saying? So this should be 0.47, 49. It's my mistake. So this should be 49. Is that what you guys were saying? Yeah, okay. Yeah, I just saw that right now. And so then the correct answer should be 0.644. I see. 0.644. I see what you guys are saying. So yeah, this should be 0.7. So please be mindful, guys, as it's very easy to confuse the decimals. Just make sure you are consistent with the different probabilities. Okay. So now let's do this last one. Given that Joe is late, find the probability that it didn't rain. So would you guys be able to do that? Probability that he's late, given that it didn't rain. How would you quickly set up the Bayes formula here? This should be a little bit quicker now, I hope. No? Okay, so the probability, so what would this look like as a conditional probability? The probability that L intersect N over the probability that N occurs, right? So then what's the probability that wait, given that Joe is late? What is the condition about? Given that Joe is late, oh, this should be the opposite way. Pardon me. This should be N given L, right? So this should be L. So L, he's late given that it doesn't rain, probability that it doesn't rain, plus the probability that he's late given that it's rainy, times the probability that he's rainy. And then up here would be the probability that L given N times the probability that it doesn't rain. This is Bayes' formula again. So I know that he came late. I just want to figure out if it rained or not. So that's what this means here. So I have all this information, don't I? I have the probability that he's late given that it doesn't rain. I got 0.1. The probability that it doesn't rain is what? 0.3. So just be mindful of the decimals again, probabilities. Then I got this here again, probability of he's late given that it doesn't rain, times the probability that it doesn't rain, plus the probability that that he's late given that it rains, which is exactly 0.3. Probability that it does rain is 0.7. So if you find what that is, this is 0.03 over 0.03 plus 0.27, 0.03 over 0.30, right? And 0.03 will be what? 0.03 divided by 0.3 will be 0.1, right? All right, guys. Oh, you're right. Look, listen, guys. Don't feel bad about saying, "Hey, you got this wrong." Really, it shows me that you guys are paying attention. All right, so don't be shy to say, "Hey, you got this wrong." It's no problem with me. So yeah, so this should be an eighth. So this is 0.125. Okay, thank you, Fernando. That's fine. Um, as you can tell, sometimes the arithmetic mistakes occur all the time. Even people up here on Zoom trying to explain stuff. Because I wrote this somewhere else. Did I write this somewhere else? Oh no, that okay. So okay, that's good. I didn't write that there. Okay, good. But again, the most important part of all of this is understanding conditional probability and how that morphs into what's called Bayes' formula. How Bayes' formula is really just conditional probability, except that now we're dealing with this thing called total probability, which is connected to the conditioning of or the partitioning of a sample space. So these problems they may appear a little strange at first, but then eventually start to get into the swing of it. And you start to expect already what's going to be the mutually exclusive events, what you're going to be conditioning upon, and then how this formula is being applied. But my main concern, when will this recording be uploaded? Well, I'll try to do this immediately. So the moment I stop recording, which is right now,